All right, well, today we're going to start the various discussions over key principles in chemical engineering, starting with fluid mechanics. We'll probably spend today and maybe some of next Monday talking about fluid mechanics, then we'll move on to heat transfer, then reaction engineering, and finally separations. That'll probably be the next 3-4 weeks. And then hopefully right before spring break, we'll start having discussions on troubleshooting and debottlenecking and putting everything together. So for today's lecture, we're going to be looking at wait a second. I think they're working fine. Your TV on. Okay, now we got all the TVs working again. We're going to be looking at mass, energy, and momentum balances. Within process fluid mechanics. So the most general way that we can look at this is for analyzing a control volume of a known mass, M, and we can analyze this control volume of interest as a collection of inputs and a collection of outputs. And for any known control volume, if we can assume a steady state condition, with no accumulation, we can state that any flow in is equal to any flow out. Now, this might seem almost crudely elementary. However, there are some really strong points that can be made with this principle, particularly as it applies to a processing facility of any kind. A good example I would think of is a steam header. If I'm wanting to supply steam to various points in my plant, I have to ensure that the amount of steam consumption that I want to have in my plant can be matched by an appropriate steam generation. What does that mean for a facility? Well, that means that without any sort of major alterations to generation conditions, you have a finite amount of steam being produced in a plant. At the same time, if I make adjustments and I want to use less or more steam, I have to find ways to make my system flexible. So how do you think you can have a steam generation system that is flexible to process conditions? Well, one idea is to produce excess steam of a certain percentage, let's say 10 to 15%, monitor the pressure, and when the pressure exceeds a certain value, you vent the excess steam. And so you essentially just produce excess amount of steam and vent a little bit of it to ensure that you have a little flexibility built into your plant. And what do you see in a lot of process facilities? Steam vents just kind of going off throughout the day, right? And that's why, you know, because if you all of a sudden need a lot of steam to make up for an issue in a temperature being off by a few degrees Celsius, you want to have a little flexibility built into your plant. And so you accept that loss. Why? Because you want to ensure that you have confidence in your material balance. Some food for thought, even when looking at something as simple as the garbage in is garbage out. Now we could extend this and say, well, if mass in is equal to mass out, and I know that mass is equal to the fluid density times its velocity times the flow area, I can arrive at the continuity equation. Which states that density in, velocity in, area in is equal to density out, velocity out, area out. And if I wanted to be extremely generic, I can do it over all inputs and outputs, right? I can just perform a summation. For most systems, we're only looking at a few inputs and a few outputs. But you can imagine complex fluid systems having to account for all the inputs and outputs can be a little tricky. Now, if we have an incompressible fluid, that implies that the density isn't going to change appreciably throughout the process, such that we can state the velocity times the flow area at the inlet is equivalent to that at the outlet. Now for compressible fluids, we can't make that same distinction in terms of the density not changing. But what we can say for compressible fluids is that the product of density and velocity is equivalent, which we call a mass flux, which is just simply a flow rate over a flow area, hence a mass flux. And so we can say that for most systems, the mass flux is conserved. And we can apply this for all inputs and all outputs, which becomes really helpful when we're wanting to account for flows within natural gas, steam, air, those types of lines within a process facility. And so we can say that mass flux times our areas are equivalent. All right, so let's look at an example. So if I have two crude streams of oil mixing, and I apply my continuity equation to estimate the volumetric and mass flow rates of the unknown stream. Why don't you guys work in your groups? Kind of get some practice doing problems. Working together, stretching the brain. Kind of like this, because I think you guys are the first group that took my 317 as junior. So this is actually legitimate review instead of when I taught it to seniors and it's literally the next test. Yeah. Because it makes me feel like
For specific driving, I'm pretty sure it's 1,000 an hour. I'm working on. 157.8. I was looking at jobs other day. On that like that. Just for like project engineers. And they want like 5 years of experience.
Yeah, funny thing about the entry level job, they want you to have the.
Like, are these all posted?
Yeah, I saw a post the other day, it was like, it was somebody took like a little piece of that, and one was like minimum education requirements, and that's. It was like salary, $50.
Yeah. I heard it.
Okay, let's see how well everybody did. All right. So for this example, we had, what was the flow rate here? 0.006 cubic meters per second. Flow rate here is 0.009 cubic meters per second. Diameter was 7.8 centimeters. 10 centimeters. I'm looking for volumetric flow rates. And then here I'm looking for velocities. Okay, so looking at it, I see two inputs, one output based on a mixing node. So the volumetric flow rate is going to be 0.015 cubic meters per second. Knowing that the specific gravity was what, 0.86 or 0.89, excuse me. That means that the density is 890 kilograms per cubic meter. So the mass flow rate is approximately 13.35 kilograms per second. That leaves finding the velocities for 1 and 2. I know that the mass flow rate is rho UA and the volumetric flow rate is U over A, which means U1 is equal to the flow rate of 1 over the area, or about 0.006 cubic meters per second over 0.00477 square meters. So you got about 1.26 meters per second. For stream 2, following the same approach, U2 is equal to the flow rate over the cross-sectional area. So I get 0.009 cubic meters per second over its area, which is about 0.00785 square meters. And I get a velocity of 1.5 meters per second. Now, from the problem, you really can't determine the velocity of stream 3 because we don't know the diameter. But if I wanted to be fun, I could say that the measured flow rate in stream 3, velocity, is 1.4 meters per second. Now I could, with this, I can most likely estimate the pipe diameter. Why? Because flow rate is equal to U times area. If I have the U, I can find the area, which was 0.015 cubic meters per second over 1.4. Ugh, my hand can't do it today. Meters per second. I do that math really quick. Morning.
Morning.
And I get a value of about 0.0107 square meters. And with that, and since I know area is pi d squared over 4, that means d, or the diameter, is 4 times area over pi, the square root, which is equal to the square root of 4 times 0.0107 square meters over pi. And I get about 11.7 centimeters. So a lot of things you can play around with applying the continuity equation. The important thing to be able to understand is, one, whether it's a compressible or incompressible fluid, what are the inputs, what are the outputs, and then with the continuity equation, you can estimate flow conditions. Any questions on that problem? All right, if not, let's move on to energy balances. In fluid mechanics. Right, so mechanical energy balance, all of Bernoulli's, is the most important equation to consider, such that we can relate internal energy, kinetic energy, potential energy, as well as any energy inputs to our fluid. Now, some kind of big picture concepts to keep in mind, which I kind of stated, is that the first three terms denote the internal energy, kinetic energy, the potential energy of your fluid at a given state. A lot of times when we apply the mechanical energy balance, we're interested in looking between two states or between 2 points. Another way that we can think of this is by considering the concept of fluid head, where the head of a fluid, H, is equal to these values in a given fluid. And when a lot of times what we're really interested in figuring out is the change in head of a fluid between 2 points, right? Primarily for transport properties, right? So if this is H1 and H2 is at a different condition, I can calculate the change in head, delta H, by looking at the change in my 3 energy terms, right? And how do I denote those changes in energy? Typically through considering any sort of work added or head loss. And so the moral of the story is, if I'm wanting to transport a fluid, I have to ask myself, what is the energy associated with the fluid at 2 points? And what is my anticipated head loss, such that I can determine a necessary energy input such that the fluid can travel from one point to the other. Does that make sense? Now, a lot of times we just consider delta H analogous to work, because a lot of times in those systems, the change in head we're wanting to enforce is what's the energy input. And a lot of times we'll talk about this again when we talk about pumps and system curves. We're wanting to know what's the energy input versus our flow rate of interest, right? And that gives rise to pump and system curves. Is everyone following okay? I don't want to confuse anybody. All right, so some other big kind of picture things to kind of remember is we can also consider the simplified Bernoulli's in the case where there is no work or friction. Right, and so in that case, we consider simply the changes associated between pressure, velocity, and height. Some other things that we always like to keep in mind is for friction, we consider the implications for both laminar flow and turbulent flow. For laminar flow, we often apply the Hagen-Purcell equation, which states that, I'll do it in terms of skin friction, delta P is equal to 32 U mu L over D squared, which also could equal, if I wanted to, 128 B dot mu L over D to the fourth by substituting flow rate for my velocity. And for turbulent flow, I must rely on a friction factor, where delta P is equal to 2F rho U squared L over D, or (32F rho V dot squared L over pi squared D to the fifth). And it's important to kind of keep both in mind depending on if you're wanting to relate velocity to pressure or your flow rate to pressure and friction. Hopefully this is kind of starting to sound familiar. All right, so let's look at practicing applying some of these equations. So in this example, I have 2 gallons per minute of water at 50 psi being forced through a nozzle, which is discharging the atmosphere. Applying the mechanical energy balance, can we estimate the discharge velocity in feet per second? So why don't you guys work on this in your groups, and then we'll see how well you did.
14.7, maybe you just do the gauge. You get the same number. You can just say. Either way, you're gonna get the same oil. You can subtract 14.7 from 50. Or you can leave the 50. Yeah, subtract the oil.
Oh, so you still have to use that.
Yeah.
I thought you were saying you did.
I was thinking, give it next. I should have given it the gauge.
I mean, we can pretend it's engaged.
Good.
Yeah.
Then we have to pretend it was right.
Yeah.
You okay with that?
What's the little like GCC if you're routing correction?
I'll write it over here. Yeah.
Yeah, then again, yeah. It really doesn't matter.
Yeah, that's why this is simple the way it is. It's kind of like a, you know, call it 10 grams, as long as you- It's easier to just. Any questions? Yeah.
Oh, yeah.
How many feet do you
I remember reading it.
Or do you have a-
You would say that down, I don't think you would, but someone, right, down. Doesn't look like it. I guess that's what you're all the time.
Did you, so what?
Like type of area, we have a lot.
I think that.
We don't know what.
I know we don't have.
Yeah.
Also, that's not. It's like it is.
Progress. Maybe.
But it's a problem when you look. I think it's the problem is if you're not familiar with that language. The pressure standard. Unless you're working on.
I'm getting next. Oh, my God. I think that's so nice. I got a non-real answer. Oh, we matched. Oh my gosh. And do you have? A negative number. For velocity. There's only, I don't see the equation. It's talent, homie, it's talent. Oh, yeah. Like calculus. 2.5.
Yeah, I love that when you get stuff ordered.
It's not negative or imaginary, so I gotta give you that. Hold on. Oh. Oh. Seven, 9. I can't tell you definitively that because my page, that page of my notes. We'll find that here in a second. How's that? I apologize. All right, let's see how it goes. Now, I'm guessing you guys jumped immediately into the calculations and then got bogged down by a bunch of unit conversions. Yeah, okay, so here's how I like to do these problems. And you can tell me whether you think it's helpful or it's a bunch of hogwash. It's up to you. So, like any good engineer, I always like to draw the problem. This is a nozzle. This is a pipe. The flow rate is 2 gallons per minute. Pipe diameter is 1 inch. Nozzle, 1/10 of an inch. And the pressure initially is at 50 psi. Now, what am I looking for? I'm looking for the discharge velocity. And feet per second. So what I'm really looking for, if I define this as my 0.2 and inside the pipe as my 0.1, I'm looking for U2. U2 is equal 1. So what I have here is most likely a simplified Bernoulli equation. So I can write it out and say P2 minus P1 over rho plus U2 squared minus U1 squared over rho 2 plus G times Z2 plus Z1. If I wanted to, work in friction equals 0. Write out the full mechanical energy balance. The next step is to analyze my system and ask myself, what can I neglect in my equation? Well, I don't see any sort of pumps or turbines. No work. I didn't give you anything in terms of friction, and I'm just going to assume that this distance is small enough that I can neglect it. And the whole system looks fairly horizontal. There's no information about elevation. So I'm going to give those two values the boot. All right, so what am I looking for? Well, I'm looking for U2. So what I can do is say, okay, I have P2 minus P1 over rho plus U2 squared minus U1 squared over 2 is equal to 0. Now I can boot the pressures to the other side and say now P1 minus P2 over rho is equal to my velocities, right? So what does this equation tell me? This equation tells me that the pressure change that I'm seeing within my fluid is resulting in a velocity change. So with that in mind, what I can do is do some algebra and say, well, P1 minus P2 times 2 over rho is equal to U1 squared minus U2 squared. Do some more math and say U2 is equal to the square root of 2 times P1 minus P2 over rho plus U1 squared. So I didn't need to do any calculations, just a little bit of algebra with the equation. And I can say, okay, I know my discharge velocity is going to be equal to this equation. Now that I have the equation, I can ask myself, what values do I need to find? I need to find my pressure 1, my pressure 2, my density, and my initial velocity through the pipe. Now, P1 is 50 psia. P2, not really given, but I said it's discharging to the atmosphere, so I can assume 14.7 psia. And the harder one is U1. Well, I don't have U1, but I have some information I can use to solve for U1. I know that my flow rate is 2 gallons per minute. And I know that the diameter of the pipe is 1 inch. So I can convert my flow rate from gallons per minute to cubic feet per second, saying there's 7.48 gallons in 1 cubic feet. And in 1 minute, there's 60 seconds. So what did you guys get for your volumetric flow rate? Okay. 0.00445. 446. I wouldn't use too many sig figs. And then I just need to get my area or my velocity, which I know from continuity is flow rate over area. I need my area, which is pi d squared over 4, or pi times 1 over 12 feet squared over 4. Which, doing this real quickly. I get 0.00545. And this is cubic feet per minute, second. So my velocity is therefore 0.00446 cubic feet per second over 0.00545 feet squared. So about 0.82 feet per second. All right, so now I have my U1. So I can plug in and solve. U2 is equal to the square root of 2 times 50 PSIA minus 14.7 PSIA over my density. Now I'm in English units, so that's going to be 62.4 pound mass per cubic feet. Now you do have to do some unit conversions. So I have what, pound force per inches squared. So if I multiply this times 144 inches squared per feet squared, and then I need to multiply it by G sub C, 32.2 pound mass feet per pound force second squared. That should clean up my units. And then I put plus 0.82 feet per second squared for that final term. I can check it with my equation, look at it. And all I got to do is run the calculation to solve for U2. So let's see what we get. I got about 72.4. I always like to run the calculations twice just to make sure that calculator doesn't give me a new value. Yep, 72.4. So I think the 100 was a little high. But any questions on that? So the moral of the story, I would probably say, is always take a look at your problem, figure out what the equation is, and can you do a little bit of manipulation before you start jumping into calculation. I find that it's a lot easier to stay organized because a lot of times you do calculations and then you get numbers and then you go, okay, what was I using this for? And so it helps, especially when the problems get complicated. All right. Now I want you guys to take a look at your in-class problem. Problem number 1. We got to take the flow coming in now. We know that the liquid level in the tank is rising. Part A asks what's going to flow right into the tank, and part B asks what's the velocity out from the figure. We're going to practice the old. Not really. I'll give you that on the-
Is that one?
Well, it doesn't matter. It doesn't- I did it.
Interesting. I'm coming.
Problem with where it's going. He said my forward in. I don't want to go again. Okay. 4 inch, 4 12.
No, you do. So I got 0.26. Or you can get percent.
Does that not mean that you haven't had a laboratory? Yeah. So like, even though this is.
I haven't done it to the 20 yet with one of the tests.
Yeah. I got a different value for that. Yeah. That's kind of a weird system as well.
Can I check her?
Or the velocity.
0.26.
That's her velocity. Okay, I didn't know you were gonna be that big.
Yeah, and that's for velocity. For.
Yeah, 0.889.
I got it on the year week. I have the velocity level Friday.
That was the 0.889.
That number is harder than.
That's.
To figure out the.
So. Yeah, but then that one.
I thought you meant velocity, you needed like a vector or something, and I was like,
Yeah,
I didn't know we were getting that.
Yeah, you have to set it up in such a way that. Yeah, it comes out a little odd.
We have to find out the other volumetric flow rates and then figure out.
We don't know exactly how much. There's gonna be another. We don't know how much that is, and we don't know how much the volume has to be.
Yeah, double check that.
Yeah. So for the. Okay, so.
Yeah.
This is probably all one. This is one.
Mm. I forgot 4.4.
This is a
I
interesting.
use that 102 water rate.
So-
Water tank, global energy, one of those areas. That's why
Yeah, if you're not, if you're gonna be on inflow, then there's.
Something's wrong.
That's why math balances are important.
Yes.
Just to be like, well, if I have backflow, I'm reporting it. Yeah, you guys didn't realize just a simple tank coming in and out.
It's backlog.
What's the subject simple? Yeah, three must be full. Whether it was designed that way.
So it doesn't-
You got me to read it, I got it.
And this reminds me of there was like a big design. I remember there was a city that designed a big like spillway for a wastewater treatment system. They spent like $30 million on it.
Yeah.
And the spillway kept failing. It wasn't working. And so they finally broke down and hired like an environmental consultant to be like, what's going wrong with the spillway? And so he goes to the big intake valve. And he goes to the intake valve in the pipe. What he does, he pours his cup of coffee in the pipe. And the coffee goes the wrong direction. And he goes, you just gave me $1,000 for me to tell you that gravity goes that way.
I got it, 1.42.
Those are some of the fun things that you'll see. We got a correction, we got a velocity. This is one of the only times we can tell the negative velocity.
I got it, Dan. 1.42 feet per second.
Because it was designed to.
Yeah. Then my numbers are showing up here.
Oh, yeah.
I don't care what you draw it. It's the same as this.
Yeah.
So in this one, you should find that there's a little bit of backflow. All right, so how much time we have left? Not a ton. All right, so in lieu of doing the problem on the back, we might do that next Monday. I want to touch briefly on everybody's favorite, momentum balances. Now, momentum balances, just like mass and energy, has its own conservation law. Where that, the momentum in minus the momentum out plus any changes in forces equals, I'll make sure I read this right, any accumulation. And I always like to consider momentum accumulation as the derivative of mass and velocity. Because if these are all kind of rates of momentum, that's what we end up looking at systems associated with force. So I'm looking at a system of a constant mass that's experiencing some acceleration, or I'm looking at a system at constant velocity that sees an increase
in a mass flow. Yeah, MA, like M, like mass times acceleration or velocity times the mass flow rate. And this was everybody's favorite part of 317. This is one of my favorite problems, was looking at I think I gave this to the juniors on their final. I made it a softball to make them feel better. So in this example, if I look at a baseball with no mass in the pitcher's mound, I know it's gonna leave the pitcher's mound at 90 miles per hour, so that's what we're getting paid for. And it's gonna go 60 feet to home plate. And I apply a momentum balance to describe this in the x direction. Well, if I'm looking at this perspective of a momentum balance, I can make a momentum balance in the x direction. Which states simply that any momentum in minus any momentum out plus any forces involved is equal to the accumulation of momentum. So in this system, if I've got a baseball flying with its initial velocity at 90 miles per hour, going 60 feet. It's a little tricky to think about momentum in and out because first question, right? We need to find the system. For me, I would define my system. So I would draw my boundary around the baseball. And then I would ask myself, do I have any momentum in? Do I have any momentum out? What do you guys think? Yes or no? I got one yes, maybe. What do you guys think? So 50-50 odds. That's better than Tunica. All right. Well, the answer is there's no momentum in or out in this system. The only thing we actually have here is a force. And it's a drag force. The drag force is equal to the net change in momentum, which once again is either a mass of known quantity with an acceleration and or a constant velocity with a change in mass. Well, the baseball probably isn't going to change mass. I hope not. So all this really boils down to, for this system, this drag force is equal to the mass times acceleration. And I know it's a net loss of momentum, so I can put a negative. So we got F equals ma. And if I want, I can say the acceleration is equal to the drag force over the mass. And if you guys remember the equation, it looks like this. So if I know the drag coefficient, its diameter, I can calculate the acceleration. Then I can apply the old physics displacement equations to find what is the velocity when it crosses home plate.
That's a neat question on final.
Why? F equals MA.
Yeah, but it takes a long time to get to F equals MA. What is AP?
The projected area of baseball. It's really just a cross-sectional area. From the discussions we had back at 317 on drag force, it's essentially the flow projected area. All right, I think this is a good stopping point. We'll touch briefly on momentum on Monday, and we'll talk about
looking at various unit ops. We might talk about FPSH, content system pairs, compressible flow, all those wonderful things. Really quickly though, before you all leave, you don't want to lose your hair over the homework.
Are you proud of yourself today?
One thing I want you guys to kind of keep in mind for the homework is I think it's problem 1 asks about the heat exchangers and the influence. And we talked a little bit about this, the U2 over U1s, right? We did this in class a little bit. It looked like this, HI1, HO1. One of the problems asked about changing the flow rate of a vapor that's condensing. And for that system, we haven't really talked about it in this class. We might have briefly talked about it in the previous classes. Was that when you're looking at boiling and condensing systems, H is independent of flow rate. So for that particular part of the problem, there's no change in the overall heat transfer coefficient. So just keep this in mind. It's going to come up when we start looking at complex unit systems. I think it's part B, 1B. So you've kind of got like half the homework already from this lecture. Pretty generous. All right, guys. Thanks for your time. Have a great afternoon.